Okay, let's conclude this topic with some remarks on numerical statistics and graphical visualizations of relationships between two variables. And when it comes to numerical statistics of relationships, there are two that I want to introduce. That's the covariance and the correlation coefficient. And when it comes to graphical visualization, that is the scatter plot. And let's start with the concepts of covariance and the correlation coefficient. So the covariance is defined by that formula here. And you can see that it is inverse basically the sum of all the products of the deviations from the mean for x and y. And then we divide again by n minus 1. The reason why we divide by n minus 1 is similar to why we divide the variance by n minus 1. It will make it an unbiased estimator. And so again, if you look at it, so we sum up the deviations from the mean of one variable, multiply the deviation of the mean from another variable. And then we average it out. And if you think about it this way, so for example, take a look at a variable. I have observations. Let's say I take students or randomly selected people, and I look at their height and I look at their shoe size. So then, if somebody is very tall, then an individual's height might be above the average, but then we would expect that probably their shoe size is also above the average. So now we would multiply in the numerator a positive value with a positive value. And if somebody is very short, somebody has a height below the average, then we would get here a negative value, but then smaller people probably also have smaller shoe sizes, so then we will multiply again something negative with something negative, and then we get again a positive value. So whenever we expect a positive relationship, like we expect a positive relationship between height and shoe size, we will get a positive covariance. And likewise, if we have a relationship between that is inversely related, maybe we look at data, for example, between GDP per capita and infant mortality rate. So countries that have an above average GDP per capita, that are very rich, they probably have a below average infant mortality rate. So now we would multiply something positive with something negative. And likewise, countries that maybe are very poor and then have a GDP per capita which is below the average GDP per capita in our data set, they probably have a very high infant mortality rate. So we would always multiply something negative with something positive, and we will get a negative value in the numerator. So whenever we get a covariance which is positive, we can expect a positive relationship, and whenever we get a covariance which is negative, then we would expect an inverse relationship. And so the covariance can range between negative and positive infinity. And again, positive values indicate a positive relationship between two variables, and negative values indicate an inverse or negative relationship between two values. The problem with the covariance is that two covariance values, they cannot be compared because they are not standardized, meaning that they are not controlled for the variation in the data. So maybe if you have two covariances, but one is subject to a huge variation, meaning each variable has an underlying high standard deviation, and we compared it with the covariance where the variation in each variable is very small, we cannot compare them. But if we control for the standard deviation of each variable, then we standardize the data and then we make it comparable. So whenever we have the covariance and we divide by the product of the standard deviation of each variable, then we get the so-called correlation coefficient. So the correlation coefficient is simply the covariance between x and y over the product of the two standard deviations. And that standardizes it between -1 and +1. That can also be proven, but that would be beyond this more applied course. So what you should know though, however, is that the correlation coefficient is calculated as the covariance between x and y over the product of the standard deviation of x times the standard deviation of y. And again, the correlation coefficient is always defined between a value between -1 and +1. And the closer it is to either +1, the stronger is the relationship, the positive relationship, and the closer it is to -1, the stronger is the inverse relationship. Okay, so let's just do an example, and let's work with those formulas. So we have here like a variable x. So we have 1, 2, 3, 4, 5, 6 observations. So, and those might be, let's say, 6 people, and we were asking them, how tall are you and what is your shoe size, let's say. So now the first observation is a 0 and a 3. So that would be 0 on the x-axis and then 1, 2, 3. So that would be this observation. Then the next one has 2 and 3. So 2 and 3 would be here. Then we have 2 and 7. So that would be this observation. And then we have 4 and 5. So that would be here, 4 and 5. And then we have 4 and 9. That would be up here. And then we have 6 and 9, which is here. So we can already see that this is obviously a positive relationship. And if we want to add a line of best fit, it probably would be a line that looks maybe something like this. But anyhow, we are not calculating now the trend line. We will do that later. But what we want to do is we want to know how strong is the relationship between those two variables. Is it rather strong or is it rather weak? So what we do is we use the formula for the covariance, and I'll just write it down again. So we set the covariance between x and y is equal to the sum of all the products of the deviations of x from the mean times the deviation from the mean of y divided by n minus 1. So now we need to calculate first the mean for x and the mean for y. Okay, let's calculate the mean for x first. 0, 2, 4. Okay, so that's 0, 2, 4, 8, 12, 18. 18 divided by 6 is 3. So x bar is 3. What about y? 3, 6, 13, 18, 27, 36. So 36 over 6, that's supposed to be a y bar. So y bar is 36 over 6, which is 6. Okay, so now in order to calculate the covariance, let's first start with the x's and subtract always the mean of 3. So then 0 minus 3 is negative 3. 2 minus 3, negative 1. Another negative 1, positive 1, positive 1, positive 3. And of course, so here we said the mean is actually 3. And of course, the deviations of all the observations from the mean, that is always 0, right? But anyhow, because we calculate the covariance and later the standard deviation, we still have to multiply that. So let's multiply. The negative 3 squared is 9. Negative 1 squared 1, 1, 1, 1, 9. Okay, so now for y, the mean was 6. So let's first subtract from each observation the mean of 6. 3 minus 6, negative 3, 3 minus 6, negative 3, 7 minus 6, positive 1, 5 minus 6, negative 1, 9 minus 6, positive 3, 9 minus 6, positive 3. Okay, so let's square again everything. So negative 3 squared, 9, 9, well, it's supposed to be 9, 1, 1, 9, 9. Okay, so now in order to calculate the covariance, we need to multiply these two columns. Negative 3 times negative 3, 9. Negative 1 times negative 3, 3. So you see it's always a positive value suggesting, and we probably get a positive relationship, and we can see the positive relationship. So next one, negative 1 times positive 1, so that's negative 1. Positive 1 times negative 1, it's negative 1. 1 times 3, positive 3. 3 times 3, that's 9. Okay, so now what's the sum of all those products? So that's 9, 12, 11, 10, 13, 22. So that is, in the numerator we have 22. So that's the sum of all these. And now we need to divide by 5. Okay, so now we get the covariance, and that the covariance is 22 over 5, which is 4.4. So this is a positive value suggesting we have a positive relationship. But we can't really say is 4.4 a lot or not. So what we need to do next is we need to calculate the correlation coefficient, and the correlation coefficient is equal to the covariance between x and y over the product of the standard deviation of x times the standard deviation of y. Okay, so we still need to calculate the standard deviation for x. And the standard deviation for x is the sum of all the squared deviations from x divided by n minus 1. Okay, so we have already the squared deviations here, so that's 9, 10, 11, 12, 13, it's also 22. So that's 22 divided by n minus 1, so that is also 22 over 5. So that is the square root of 4.4. Okay. So now we can write that because the covariance is 4.4, but the standard deviation of x is the square root of 4.4 times, okay, so now let's calculate the standard deviation for y. So that is the sum of all the yi's minus y bar squared over n minus 1. Okay, so that is 9, 18, 19, 20, 29, 38. So that's 38 over 5, unless I made a mistake. No, that's 38. So 38 over 5, that is equal to 7.6. The square root of 7.6. Okay. So now let's just calculate this one here, and I will do that in Excel. So let me pull up an Excel sheet so we can calculate it. Okay. So let me see where we can put that. Okay, so here I have an Excel sheet, and so now let's calculate the, actually we just can copy that, copy, okay. Okay, so now let's see. So we said the covariance is equal to 4.4. Let's double check that in Excel. So the formula is, okay, so if you enter COV, you already see Excel offers you covariance.p or covariance.s. So we use the covariance.s because we work with a sample. And then it says array 1. Array 1 are these numbers. Those are the x's. Then array 2 is this one. Close parentheses. And now we see we get indeed 4.4. So let's put that here. So that's the covariance between x and y. So then we said the correlation coefficient should be equal to, I write that here, so that is equal to the 4.4, which is the variance that the covariance that we just calculated, divided by the product, so divided by open parentheses. Now we can say square root SQRT of 4.4 times the square root of the 7.6, close parentheses. So that should be the correlation coefficient, and that is, if we round it to 3 digits, 0.761. Okay, so the correlation coefficient that we now calculated was 0.761. Okay, so let's just double check again the standard deviation of x, the standard deviation of y, so equals standard deviation s of x, that's 2.09, and then we said this should be the same as the square root of 4.4, and that's the same. Now the same for y, standard deviation of s of y standard deviation s so that is 2.75, and we said that should be the square root of 7.6 equals square root of 7.6. So those are the correct numbers. And we said the correlation coefficient is 0.761. So there's also a command in Excel. So the correlation coefficient, is equal to, so the command in Excel is correl, and then again array 1, array 2. So now we should get 0.761, which we do. When we round. Okay, so now we have seen how to calculate the correlation coefficient and the covariance, and the correlation coefficient is obviously the more meaningful one because it can be interpreted and it can be compared. So now you know how to calculate it. So you see here the formula again. The correlation coefficient is simply the covariance divided by the product of the two standard deviations, and it is always between -1 and +1. The covariance is also a little bit insightful in the sense that whenever you have a positive covariance, you can conclude, well, there is a positive relationship. If it's a negative one, there's an inverse relationship. But you typically want to report the correlation coefficient. And of course later, when we go into more advanced material, we also introduce another measures of relationship, which are regression coefficients. But for now, we have learned enough about numerical statistics of centrality and dispersion, but also relationships, and let's just stop here and stop here.